Awesome. So welcome everyone. We're excited for this presentation here with Joshua Liberman on Earth 2.0. My name is Osha Rose, and I'm the Adult Programming Coordinator here at the Rockport Library. So happy to have you all joining us virtually. Josh Lieberman is a second year PhD student at the University of Arizona's Wyant College of Optical Sciences. So his research involves imaging planets outside of our solar system with ground-based telescopes, and he is going to share with us about that research. And I'm so excited. Welcome, Joshua. He's hailing to us from the West Coast. I'm very excited to have you here. So welcome. Welcome, Joshua.
Thank you for having me, Osha. Um, as Osha mentioned, my talk is called The Search for Alien Worlds from Earth's Largest Telescopes. So just to briefly outline this work, um, I'm going to start by just giving a bit of my background and how I got into studying, well, astronomy and telescopes, and specifically the instruments that power these discoveries within astronomy. Um, and so then I'll get a bit into these telescopes and instruments. I'll next talk about these planets outside of our solar system that we call exoplanets and how people find them. And I'll then talk about this cutting edge technology that I use to try and find Earth-like planets. And finally, I'll talk about the instrument I currently work on called MAG-AOX. And lastly, I'll just talk about some future prospects and some, exciting upcoming astronomy research. So just to give a bit of background, I was interested in astronomy from when I was little. So my mom had a mad scientist birthday party for me. I think this was when I was in third grade. So in this picture, I think I can be seen submerging an egg in vinegar. Um, and then I graduated from Reading Memorial High School in Reading, Massachusetts in 2018, which is, I guess, 7 years ago now. And I attended Colgate University, which is a small college in the middle of New York State. And it was here that I became interested in astronomy and kind of the instruments behind these astrophysics discoveries. So I started in the first year after, in the first sorry, I started in the first summer after my first year of university, and I did research with household cameras, and specifically trying to use these cameras to look for stars and basically look at stars and monitor how they change in brightness. And through this, I joined a larger citizen science project that was trying to use these household photography cameras to find exoplanets. So I was really interested in trying to manipulate the settings and really push these household cameras to like kind of transition them from being pretty photography devices to actually collecting scientific data. And from here, with this interest in instruments, that led me to the intern at the Keck Observatory in Hawaii. So Keck is actually composed of two telescopes, and these are the second largest telescopes in the world at around 10 meters in diameter. And so you can see here on the right, this is me standing in front of the giant telescope dome that is one of the Keck telescopes. And also during this internship, I had the opportunity to do some observing. So modern observing in astronomy oftentimes looks like this, which may be a bit anticlimactic, but a lot of times when you're using a telescope and participating in observations at one of these large professional telescopes, you're often doing it over Zoom. So here, this is what we colloquially call pajama observing. So in the foreground is my squishmallow, and then in the background in this image is actually the center of our galaxy. specifically the black hole at the center of our galaxy, as viewed through this Keck telescope. And here I was participating in these observations as a guest. And so after this internship at the Keck Observatory, I spent a year or so after my after obtaining my undergraduate degree at Caltech as a researcher. So this marked my first hands-on experiment experience with the instruments and with instrumentation um, at a sort of professional level. So you can see here on the left, this is me working on setting up an optics table where we were trying to conduct experiments to develop the technology that we can use to take pictures of these planets that we want to see. And then on the right, this is me again, pajama observing with that same telescope, the Keck telescope. And this time, this was using a special instrument that I worked on at Caltech, where we can not only take pictures of planets, but also determine what's in their atmospheres. And I'll talk a little bit more about that later in this presentation. And so after kind of bouncing around Colgate to Keck to Caltech, I started my PhD at the University of Arizona in fall of 2023 in the College of Optical Sciences. And additionally, just to kind of give you a sense of the travel that's involved in astronomy and instrumentation, my group in Arizona then travels from Arizona to Chile, where we conduct our observations, and then back again. So there's a lot of travel in astronomy. And why do it? And the easy answer is just that, like, the best observing sites in the world are often found at more remote locations. So, why do we build these telescopes in remote locations and why not Massachusetts? So, I did do a bit of research prior to this presentation, and I believe Rockport, Massachusetts has one of the darkest sky parks in Massachusetts for stargazing. I think it's called Halibut Point State Park. But the issue with, for example, doing your astronomy in a state like Massachusetts, as all of you well know, is that there's a lot of inclement weather. So in winter, it's pretty much you're going to have a lot of really cloudy nights. Um, and so that's just not ideal for professional astronomy, where you really want to find a location that will give you the most clear nights possible out of the calendar year. And so, what are the things we look for in building these telescopes? Well, one is clear weather. So, this is the observing site that I use with my group, and this is in Chile's Atacama Desert, which is also the driest place on Earth. And so you get really clear weather and you never have, or you have virtually no humidity at this site. And also we look for dark skies. So this is the Milky Way over Mauna Kea, which is the mountain that these two Keck telescopes are situated on. And so dark skies are, of course, really important for astronomy. And these two sites, Mauna Kea and then the aforementioned Atacama Desert site, these are two of the darkest sites in the world. Additionally, you really want to be at a high altitude and above the clouds because clouds in the atmosphere in general is a real nuisance in ground-based astronomy, and I'll talk a bit more about that later. So here in this image, you can see clouds beneath the Las Campanas Observatory in Chile. So what do these professional telescopes really look like? Well, to do that, I'm going to take you inside the Keck telescope. So what you're seeing here is the Keck telescope moving into position, and you're going to see in the background here, if I can activate maybe a laser pointer, we'll see. Well, if not, I don't know if you're able to see my cursor, but if you can, in the background here, we have our giant Keck telescope mirror. and made of this interesting honeycomb structure that I'll be talking a bit more about briefly. And then in the very foreground, you have what we call a secondary mirror. So the light is going to bounce off this first mirror and then go into our second mirror. And finally, it'll come to its last spot in the center of this telescope mirror in this hole here. And that's what we call the tertiary mirror. And from there, it'll go off to our various telescope instruments. So let's talk a bit more about this mirror specifically because it is very cool. The Keck mirror is actually not just one solid piece of glass, but rather is made up of multiple segments that you can see on the back, multiple hexagons. And that's because creating mirrors this large on a scale of 10 meters is a massive technical challenge because when mirrors or glass gets this big, you really need to get creative in how you're going to create your telescope mirrors. So rather than make a mirror from a single piece of glass, one common approach is to make a giant mirror composed of these multiple smaller mirrors that we call segmented mirrors. And so here you can see one of these individual segments in a polishing room. And so the and with this technique, you can build much lighter mirrors, much lighter in weight, and mirrors that are easier to transport. So you can think of each of these hexagonal segments as a sort of a puzzle piece. And so then when you're transporting this whole giant mirror to your remote observing site, rather than carry the mirror in its full size, you can kind of take the individual puzzle pieces, individual segments up to the top of your mountain, and then assemble it at your telescope, which is a lot more convenient. Another really cool feature about these modern telescope mirrors is they're outfitted with all kinds of electronics on the back of each of these segments. And the purpose of these electronics is basically to push and pull on our mirror slowly. Because over time, due to subtle changes in temperature inside your telescope dome, your mirror or mirrors are going to bend and flex. But because we want to treat this as one solid mirror, anytime a single piece bends and flexes, these electronics tell every other piece to move in the exact same way. So in that way, you have multiple smaller mirrors all functioning as one collective unit. Additionally, I mentioned a bit this that tertiary mirror in the back of our telescope. So after the light goes through that, it's going to go into Keck's, one of many of Keck's instruments. And so these are a few here. And these actually slide along rails. And so you're going to slide them into this tertiary, this third mirror in your telescope. And as you can see here, these telescope instruments get to be pretty big. And here, just continuing with that, this is another view of that tertiary mirror. And this is the port that the instruments at the Keck telescope are moved into. And so this is where the light is coming in when when you're pointing at your star or object of interest. And so now, how do astronomers find exoplanets, or these alien planets with large telescopes? Well, to answer that question, we need to take a step back and ask ourselves, well, what is an exoplanet? And put simply, it's any planet that's outside of our solar system, so outside of the 8 planets that we know in our solar system. And here on the right are a few of my favorite artist conceptual drawings of some known exoplanets and what they might look like. So there are multiple ways in which astronomers find these planets. And the first method is what we call the transit method. So In this method, you're going to look at the light from a star and monitor its light over time. And whenever a planet passes right in front of the star, right along your line of sight, so where you're looking at the star, you're going to see what we see here in the lower left. You're going to see a dip in the star's brightness. And so in this way, you can indirectly identify a planet. So you're not actually seeing the planet in this method, but you're seeing that something um, roughly planet-sized or so is causing a dip in the brightness of your star. And from that, you can infer the presence of a planet. The next method we'll talk about is also a very popular method of finding planets, and it's also indirect. And it's what we call the radial velocity method. And so this method utilizes two properties in physics called redshift and blueshift. And basically, blueshift is, well, we kind of refer to this colloquially as the siren effect, where when an ambulance, for example, is driving towards you, the sounds are more high pitched. And that's what we call in physics blueshift. And then as the siren or ambulance is moving away from you, the siren sound is lower pitched, and this would be considered redshift. So in the same way, you can observe the influence of a planet on a star. So when the planet tugs the star towards us, we see the planet appears, or we're going to see the star appear bluer in color. Whereas when the planet tugs the star away from us subtly, we're going to see the star slightly turn more red in color. And so again, this method doesn't give you a ton of information on the specifics of the planet itself, like what's in its atmosphere, but it does tell you that a planet is orbiting a given star. And so this next method is probably well, definitely my favorite method here. And this is called the direct imaging method. So what you see here is actually one of my favorite image sequences in all of astronomy, one of my favorite videos. And this is a time lapse. So what you're seeing here are actual planets, these dots, moving around a central star. And this is over a period of time of about 7 years. So in the center of this image, we have what's called a coronagraph or a starlight blocker. So something we put in to remove all this extra really bright starlight you see that might prevent us from seeing these little dots or planets move around. And here you can actually identify 4 planets moving around this star. And if you're familiar with physics, then you'll also see in this video, this is a really good illustration of a fundamental property in physics, where objects that are closer to a star move more quickly, and objects that are further away move more slowly. And you see this in the time lapse, where if you look at these planets D and E, you can see that they get almost like they pass all the way through this red circle and almost out of it, whereas this planet B in the upper left is kind of moving a lot more slowly over these 7 years. And so what can we do with this technique, this direct imaging technique? Well, the reason why it's really powerful is, as you saw, because we're getting these pictures of the planets directly, we're directly capturing light from the planet. And with that light from the planet itself, you can learn a lot of different things. So you can, for example, you can feed all that light coming in into an instrument called a spectrograph, which is an instrument that will tell you what is inside the planet's atmosphere. So you can tell from this method that the planet might have water or methane or carbon monoxide, for example. And so using this approach, we can determine whether or not alien planets we're looking for are actually suitable for human life. And there are a few criteria that we generally go by when looking for Earth-like planets, and it's what we call the Goldilocks zone. So we know from living on Earth that to have life, our planets must be roughly Earth-sized, and they also have to contain liquid water. So, for example, there are planets we found that are too close to their star, and so these are too hot to have any water. And then there are planets further away from their star that are much too cold to have any liquid water. So you really want to find this region, the Goldilocks zone, that we consider to be just right. So then why haven't we found any of these Earths just yet? Well, the simple answer is that it's really difficult. So one of the main reasons is that if you ever look at the stars in the sky, you're going to see them twinkle. And this twinkling is caused by moving pockets of air. And the reason for this is that Earth's atmosphere is causing our star to wiggle a bit in the night sky. And that's really bad for astronomy, as you'll see shortly. And it makes things really challenging. So you might know the show Dancing of the Stars, and or Dancing with the Stars. In this case, um, we're looking at Dancing of the Stars in our work. And this is one of the main challenges we face when trying to conduct astronomy with big telescopes on the ground. So to illustrate this, what we kind of expect from just taking pictures on our giant telescope are pretty images like this, but the reality of what you get looks a bit more like this. So this is a telescope taking images of a star, and all this blurring and smearing around and wobbles that you see in this clip, these are all from Earth's atmosphere. And so you can see here that the atmosphere has ruined our image. So in order to correct for this, we need to utilize a technology called adaptive optics, which is a fancy system that reduces these atmospheric distortions and allows for clearer images of astronomical objects, sort of like giving your telescope a pair of glasses. So in this image here, you can see that on the left, we have this sort of blob without adaptive optics. But then when we turn on our AO technology, you can all of a sudden see two stars next to each other, whereas you couldn't see them before due to these effects from the atmosphere. And so just to demonstrate what this system looks like, you're going to have light that's coming into your telescope, and as it enters the telescope, it's going to hit what we call a sensor, a wavefront sensor. And this is going to measure the atmospheric wavefronts in their shapes as they come in. It's going to send that information to a computer, and then the computer is going to tell a fancy mirror that we call a deformable mirror to basically assume a shape that will cancel out these atmospheric wavefronts, or this wobbly effect. And so this is, as you can see, a pretty complicated system where we have to utilize really fast computers to keep up with Earth's constantly changing atmosphere. And we have to make use of these fancy movable mirrors and these sensors. So what do these mirrors look like in practice? Well, you can see here that the mirrors we use for correcting the effects of Earth's atmosphere are much smaller than these giant telescope mirrors you saw before, whereas these are maybe the size of a coffee coaster. And what you can see in this video here, you see this shimmering effect. That's not smoke or anything like that passing in front of the mirror. That's the mirror itself wobbling when we have a computer send commands to it to assume certain shapes. So in this video, this particular deformable mirror is actually moving a lot more slowly than when we typically use it, where it's trying to correct really quickly. And so in reality, this mirror is going to move up to thousands of times a second. And so you can imagine these fancy specialized mirrors are really expensive, and they have lots of little motors glued onto the back to push and pull on the glass to assume these fancy shapes. And so, is this AO technology that I just talked about good enough to detect Earth-like planets? And unfortunately, the answer is still no. So the this leads us to our second problem, which is that stars are really bright and planets like Earth are not. Planets are very faint, and Earth-like planets like ours are actually 10 billion times fainter than our sun. So people often liken the challenge of seeing a faint planet like Earth next to a bright star like the sun as being similar to trying to um, see a firefly next to a lighthouse from, say, 30 miles away. And so as you can see here, we have this really bright star, which is preventing us from seeing anything else. And the only way we can see our planets is to take away some of the brightness. So this is a simulated image here. And what you see after you block this starlight, all of a sudden, you would be able to theoretically see Saturn and Jupiter in this image. So we need a way to block all of this starlight. And how do we do that? Well, we use a device that we call a coronagraph, which is kind of like creating an artificial eclipse. So we're going to take an optic, so either a piece of glass or some kind of piece of metal, and use it to block out as much starlight as possible and see the planets next to these stars. And all of you right now actually possess a very simple form of a coronagraph, which is your thumb. So if you hold your thumb up to the sun, you can block out the sunlight. And that's effectively what we try to do with these coronagraph optics that we build. We try to block out the starlight and see objects right next to, in this case, your thumb, but in our case, right next to this star that we've uh, blocked the starlight from. So, just to recap what we've talked about so far, to build a planet imager or image Earth-like planets, we need a good telescope location, a system of desmearing our images, and a coronagraph or starlight blocker. And these are a lot of technical hurdles to overcome, but luckily for us, we happen to have such an instrument that checks all of these boxes. And enter MagAOX, which is a system we've developed at the University of Arizona to image these exoplanets around bright stars. And so you can see here we have a pretty complex system. You have this giant box on the left, and this is filled with all of our computers we use to run very fast calculations in real time and correct for atmospheric disturbances. And then you have all these cameras and mirrors on the inside of our instrument. And so the acronym doesn't entirely work, but you kind of have to be a bit creative. It's the Magellan Extreme Adaptive Optics System. So what is extreme AO? So you can think of it as that regular AO I talked about, putting glasses on a telescope and just making that a bit more extreme. And you wouldn't be that far off in your interpretation. But here I included a series of comparison images of this is what a star looks like without AO. And then you have in the middle with AO, which is what most modern telescopes have at this point, this AO system. And then only a few telescopes, maybe three or so in the world, currently have instruments that do this on the far right, called extreme AO. And so in comparing these images, you see in this middle one, we have a lot of these blobs, this sort of halo of light around our star. And this is all created by effects of the Earth's atmosphere, kind of scattering or smearing our light. And then in this extreme AO image on the far right, you see that a lot of that halo and those residual starlight effects have been removed. And so the ultimate impact of this is that if there were a planet closer to this star, it would be easier to kind of see it or tell it apart from our star with this extreme AO system. So here's just another inside look at our instrument. And so you can see we have this blue and pink is the path taken by the light after it enters our telescope, which in our case is the Magellan Clay 6.5 meter telescope in Chile that I'll talk a bit more about shortly. And the general idea of this slide is just to give a sense of how complex these adaptive optics systems really are. And it looks a bit messier in reality because this diagram doesn't include all the various cables and wires coming out of each of these devices in the picture. So how do we get such an instrument from Arizona to Chile? Because we do, at the same time as when we want to use it, we also want to bring it back to our university for upgrades. And so as far as we know, we're the only group that does that. We actively transport our instrument back and forth from Arizona to Chile. And it can't walk, unfortunately, and that would make our job a lot easier. But instead, we moved this instrument using graduate students and a lot of shrink wrap. So we have semi-annually a bit of a packing party. So what you're seeing here is our giant instrument inside of our lab, and then we're preparing it for its intercontinental voyage. So here we start by shrink wrapping it. So wrapping our instrument up like a gift. And then once we're done with that, we're going to take down this clean room structure that you see here. And finally, we have to take out a giant crane because this instrument weighs something like 2 tons or so. And we lift this onto a cart. And then from that cart, I will just fast forward ahead. We move our instrument onto this shipping platform where finally we pack it up into its crate that we have to lift on top of the instrument. And then additionally, we pack up all of our electronics and computers into yet another crate, as shown here. So finally, after all of this, we have arrived, along with our instrument, at Las Campanas Observatory in Chile, and we place our instrument on this giant telescope you see here, which is the Magellan Clay 6.5 meter telescope, as I mentioned before. And in the background of this image on the right, you can see our instrument kind of peeking out, and that's our instrument connected to the telescope. And so here's just another view. This was me just viewing our instrument on the platform, on the telescope platform. And we also have a lot of stickers for our instrument to commemorate each of our observing runs, because it's very important that your telescope instrument has a lot of stickers to personalize it. The Once we're all ready to observe, we unfortunately have to wait in line when heading up to the telescope because there are wild horses amongst other animals on the mountain that also enjoy astronomy. So we have to wait in suspense behind our wild horses, and then we finally get to the telescope, and it's finally ready to open. So here in these time lapses on the left and right, you can see the telescope dome opening and the telescope preparing for another night of observing. And so I always think it's really impressive to watch these humongous structures just kind of uh, move on their own. And you can see here their telescope is moving into position to observe its first star. And so finally, we're ready to use our instrument on sky. And I'll just first let the results speak for themselves. So that right there is one of the clearest images you'll ever see straight off of a ground-based telescope, off of a professional like 10-meter class ground-based telescope. And you can see here, I'll just play this clip again. You have our star, like I showed before, very wobbly. And then when we turn on our system, we completely freeze the star in place. And now, because I think this image is really cool, let's examine it in a bit more detail. So we have various spots. We have our star in the center, and then we have these various spots around it. And what do these spots mean? Well, these are just optical effects from our mirrors that bend. So we have 1, 2, 3, 4, 5, 6 here. But then you can see here we have an extra spot. So what is that? Well, that is actually a planet. Or, sorry, not a planet, but a companion star, and it's orbiting our main star. And so we were looking at Pi Pup A, and then after turning on that AO system, we've turned our star from a blob into actually two stars that we're able to see, Pi Pup A, and then the smaller dot over here, Pi Pup B. But we can also do a bit better with our extreme AO system. So in this video, you will see us increasing the strength of our correction. And so you see these kind of dots moving around that pink pattern, and you're going to see that clear out, basically move outward in kind of this dark ring structure. And that's us basically increasing the strength of our correction with our fancy AO system. Additionally, you see in our star, around our star, you see these kind of cross-like effects, um, sort of an X right here, and that's a fundamental property of optics, which basically tells you that you've reached the limits of your optics. Like you can't obtain a better image than one you see here. And so this is called being diffraction limited. And so you see that here with these spikes. And then if you look closely, you'll even see rings kind of around our star. And this tells us that we've basically achieved the optical perfection, so to speak. So what can we do with this instrument? Well, a few of our results we've found so far include a direct image or picture of the gas giant called HD 92987b. And this particular gas giant planet is about 10,000 times fainter than its star. And the star itself you can't see here, but it's located in the upper portion of our image, and it's currently blocked by one of our coronagraphs, a particular one that we call a knife edge, because it's really just a piece of metal that we use to cover up our bright star. And we've also observed other gas giant planets like this one here that's called Beta Pictoris b. And this particular planet is 1,000,000 times fainter than its star. So now we're getting closer to this regime in which we're able to see planets like Earth. But we can also use our instrument to look at these planet nurseries. So disks of gas and dust around a star or around a planet that are that can actually indicate where planets are forming. And so here we have a disk of gas and dust around the star HR 4796. And gaps in this star's debris disk can indicate the presence of planets forming. And just to give another sense of the complexity of our instrument, we typically use a lot of computer monitors while operating our instrument, maybe up to 8 computer monitors, because we kind of have to pay attention to all of these screens and all of these things happening within our instrument. And so just to highlight a few of these briefly, in this corner of our video here, we have a view of our bendable mirrors. And if you look really closely, particularly at that center little video, you can see this kind of black and white pattern moving across our mirror. And that pattern is actually the atmosphere itself reflected or as seen by the shapes that our mirror is taking on. And additionally, we always monitor the weather patterns while we're observing, because sometimes it can be a bit variable. Despite being in one of the best locations on Earth for astronomy, you still have the occasional patches of clouds, and that can disrupt our system. And then finally, in the far right, we have our 2 science cameras. So you can see one of them right here. And in this particular image, we were actually pointed on a star, and we had our coronagraph in, which is this kind of black square, which is blocking part of our image on the camera. And then we have all these little kind of spots dancing around in the lower part of our image. And these spots are light that's being scattered by Earth's atmosphere. And so, as you can tell, then we have a very busy telescope control room, because on the MAG-AOX team, we typically travel to the telescope ourselves to use the instrument, as opposed to doing this pajama observing method that many modern astronomers will use when carrying out their observations. So, unfortunately, we haven't found any Earths or Earth-like planets yet, and the search for alien life continues. But we have a lot of exciting prospects on the horizon. For example, this is an artist's rendition of a planet around our nearest stellar neighbor, so the star closest to our sun, which is called Proxima Centauri. And around this star is believed to be a planet that may be like our own Earth. So it may be a habitable Earth-like planet, but we don't yet have the technology to take a picture of it like the pictures I showed of those other planets. And that's because this one is a bit fainter. It's rather than 1 million times fainter, it's closer to 10 or 100 million times fainter than its star. But this is the ultimate goal of our instrument, MAG-AOX. Also along the horizon, our group is working on the atmospheric correction or AO system for a future telescope, an even bigger one that's being built in Chile by a consortium of universities in the US and around the world. And this telescope is going to be called the Giant Magellan Telescope. And this one will be 25 meters wide, roughly. But additionally, you don't have to take pictures from the ground at all and be limited by Earth's atmosphere. Rather, the most promising method for eventually finding Earth will actually be to take pictures from space with a dedicated space telescope. So here's a picture of a planet around a star that James Webb Space Telescope took, which is the current telescope that many astronomers are using to collect their data with. It's a space-based telescope, which is basically the successor to Hubble that many of you have probably heard of. And so this particular planet that this James Webb Space Telescope took a picture of is actually the coldest and oldest planet that we have ever directly observed, which is pretty exciting. And so, in order to carry out this space-based mission of finding alien Earths specifically, NASA is building its next flagship telescope called the Habitable Worlds Observatory, with the goal, at minimum, of being able to take pictures of planets that are the size of Earth around stars like our sun. And this telescope is set to launch within the next few decades. And so that's roughly the timeline, I would say, for when to expect um, news about alien planets or like planets that are like Earth and we know them to be habitable. So, just for some concluding remarks, as I said in this talk, direct imaging is the key to finding alien planets because using this method, um, we can collect this light from the planet itself, and then we can determine what is in the planet's atmosphere. Additionally, I talked about how astronomers can take pictures of these planets by correcting for the atmosphere on the ground and also blocking out starlight. And finally, I would say we expect to find these Earth-like planets within the next few decades. And so here is just a slide showing all of our team members because it takes a really big team to run our instrument, and we are always growing. And so it makes it a really exciting time and an exciting group to work with. And so I'll just leave you with this and thank you for listening.
Thank you, Josh. That was wonderful. So grateful. Um, does anyone have any questions for Josh? Amazing. Like for me, it's like just to be able to see and this understanding of the mirrors and the technology. And I think I'll do the thing with my thumb and just kind of like create my own little eclipse and just think about how, oh, we have a question, how amazing
Eh,
the technology is. Margaret, go ahead.
Yeah, I just wanted to thank you for sharing your knowledge, your experiences, and your enthusiasm. And I wish you every success in the future. Thank you very much.
Thank you.
Beautiful.
Hiya, Josh. It's been a long time. Well, anyways, I was wondering the light, when I've been taught that we're seeing light that takes forever to reach us.
Yes.
So when you're looking through a telescope, I guess that it's a weird way to ask it, but how long does it take the light to reach, the telescope field? I mean, like in that last one, is it possible that that planet do you factor in the evolution, the time that that planet may actually what you're looking at because it's a long time away because of the distance?
Yeah, that's a really good question. So we typically take pictures of much younger planets, and really we treat it as kind of um, we kind of have to work with what we get in terms of the pictures we're getting. And so we interpret directly based off of the picture we see. So, for example, in this image, this is the oldest planet we've ever observed, but it's actually much easier to take pictures of younger planets. So, younger being like the light may have only taken a few million years to reach us, as opposed to like 100 million or so. So these younger planets that I show here, for example, this one, which is almost considered it could be considered like the embryo of a
Yeah.
star, like a star that's just forming. Um, so these are much younger, and younger planets are often easier to see because they're a lot brighter. And so it's much easier to see a brighter object next to our star than a really faint object. And brighter being, say, 10,000 or a million times fainter than the star as opposed to a billion. I hope that answers your question.
Yeah, no, it makes perfect sense. I just couldn't get it straight in my head. Of course, the other question is, do you ever hire people with marketing experience for better names than Beta Pictoris B? Because it really doesn't roll off the tongue.
Yeah, that's also a good question. Unfortunately, astronomers are very particular about their naming conventions. And so I don't know how much freedom we as researchers have if we, for example, discover a new planet. You usually, a lot of times, you name it after the star and then just add a letter from the alphabet, which is not very creative.
Well, I'll tell you, for being a librarian, the naming convention thing I hold near and dear to the heart. So I withdraw any criticism of the naming.
Oh, this is so wonderful. Thank you, Joshua, for sharing and taking this time. It's fascinating. We're just so excited to have had you come here. Thank you.